Okay.
Okay, so we're going to have the first lecture by Chiara, who's going to tell us about black holes and ADS.
Okay, thank you very much. So first of all, thank you very much for the invitation. Can you hear me, by the way? Is the microphone working? Okay, okay. Very good. So thank you so much for the invitation. So in these lectures, I will give a bit of a survey of all the various thermodynamics and microstate properties of black holes in anti-de Sitter. So there were many different developments that happened in the past few years. And of course, the study of black holes in anti-de Sitter is motivated by the ADS-CFT correspondence, which I'm assuming you're well familiar with. So there are many different features that I want to highlight in this lecture. So of course, highlighting all of them is a bit of a daunting task. But what I will focus on in my lectures, so I was not aware of the level at which I should have given the lectures, but I'm assuming the first lecture will be something like will be at a basic level. I will recap features of black holes in just the Schwarzschild solution, for instance, their thermodynamic properties, and also how the thermodynamics of black holes in anti-de Sitter differs from the thermodynamics of, for instance, a Schwarzschild black hole in asymptotically flat space. So this will be part of my first lecture. It's also the last lecture of today, so I thought I would keep it a bit more simple, let's say. And from tomorrow, I will give you a bit of a survey or a review of the various supersymmetric black hole solutions in anti-de Sitter. So this will be a survey of the developments of the past, let's say, 10 years. And I will give you some explicit examples on how to construct these solutions, at least the solutions that are the simplest, the static ones. I will give you also some exercise that we can do together, or at least I can start doing, and then you can complete it probably at home or during the lecture if you want. And so I will explicitly construct, give you an example of how to construct the clean spinor on this solution. So at least you can say that once in your lifetime you have constructed a clean spinor, and this is something that applies for sure to these black holes, but the level how to solve the supersymmetry equations is also valid if you want to find some other kind of configurations, such as vacua or also domain wall solutions. So it's a more general technique that I will specify to this particular case. Moreover, since there were lots of developments in the past years that indeed, they were aiming and they successfully reproduced the entropy of black holes in anti-de Sitter, so black holes which preserve supersymmetry, that I will construct in the second day. On day 3, I will explain how to rewrite their entropy in a very suggestive form and how to actually account for the microstates that give rise to black hole entropy via computation in the dual field theory, via localization. I'm not going to go too much in details on how the localization computation is done. These lectures will deal mainly with the gravitational part and with the supergravity part. And finally, in the last days, I will give you an overview of which kind of black hole configurations there can be in the Sitter. What is the shape of what is the possible shape of the horizon for a black hole in anti-de Sitter? So we know that in asymptotically flat allows for many different kind of configurations. For instance, black holes which are multi-center, or even in higher dimensional, you can have black rings and black Saturns. So I will give you an overview of this solution, and I will give you some physical motivation whether we can expect this solution to exist or not in space-time with a negative cosmological constant. So do black Saturn or multi-center black holes in anti-de Sitter exist? So that would be the aim of my last class, the one on Friday. And during the lectures, I will also give some exercises, so then you can just you can do them and then ask me, or we can try to make them during the lectures. So first of all, well, I'm going to start with something very basic, of course. So I think that you all know what a black hole is, but in any case, so a black hole is formed by the collapse of very heavy stars. So, and a black hole horizon is characterized by the presence, a black hole solution is characterized by a presence of the event horizon, which is a surface that marks the point of no return, meaning you fall inside a black hole. If you cross the event horizon, there is no hope for you to come back. So a black hole indeed is very as we mentioned, so the first solutions of black hole were found by Schwarzschild in 1916, and it describes a static solution with mass, which denotes indeed shows an event horizon. So they are very, these objects are very like challenging to explain from the theoretical point of view. They exhibit many intriguing features, in particular the fact that they exhibit some thermal or thermodynamics behavior. However, they are not just a theoretical, just a theoretical object, because we have seen that indeed they exist in our universe. Multiple experiments such as LIGO, or lately also there was a picture of the black hole at the center of our galaxy. So these objects, they really exist in our universe. So that's something that we really prompts us to, our motivation to study them. We'll study them mostly on, my talks will focus mostly on black holes, which have some specific symmetry properties. So therefore, we don't expect to find the black holes that I'm treating in these lectures in our universe. Therefore, we might expect that by explaining some features at the very fundamental level, such as their entropy, these features might also be shown to a certain extent also by astrophysical black holes. Indeed, some of the black holes that I will study that I will let's say analyze, for instance, on day 3, they are rotating, and they share at least the near horizon geometry of a rotating black hole, which you can find actually in our universe. So as I was mentioning in this lecture, I will tell you more about the thermodynamics of black holes, but in general, I study black holes in anti-de Sitter for many different reasons. So for instance, you know that ADS-CFT is a duality of the form weak-strong. So one can study strongly coupled field theory phenomena by means of black holes in anti-de Sitter. So you can model phase transitions in the dual field theory by means of phase transitions of ADS black holes. And I will give you some examples of this during this lecture of today. But also black hole entropy provides us, on the other hand, one can actually use the dual field theory description provided by ADS-CFT to learn something more about black hole entropy. And black hole entropy indeed provides very useful quantitative information about the theory of quantum gravity. And as we all know, formulating a theory of quantum gravity has been one of the outstanding problems for the past 40 years, let's say. And one of the successes of string theory was indeed explaining the microscopic entropy for specific classes of black holes. But so let me just begin now with a few remarks. So first of all, in general relativity, a black hole is characterized, I'm talking about simple black holes in asymptotically flat in theories of general relativity. So a black hole in general relativity is a simple object. So indeed, this is characterized by its mass, charge, and angular momentum. And the fact that this is simple, let's say, the theory that needs to explain this. So according to classical gravity, a black hole is a very simple object. It's something that stays there. It cannot be characterized by anything else other than these conserved quantities. However, a black hole is also a very complex object. Indeed, as I will explain before, it possesses really huge entropy. And explaining this huge entropy falls into the realm of quantum gravity, which, for our purposes, will be explained by string theory. So it turns out that indeed, from what we have understood in the last years, a black hole is not simple because it is indeed an elementary object, but it's simple because it's a thermodynamic ensemble. So it's indeed specified by very few parameters. And like a thermodynamic ensemble, specified by the temperature, specified by some entropy and some energy. So let me first start with writing down the solution. So I'll start with very basic things. You can tell me if all of this is really trivial for you. So the Schwarzschild solution is a solution of the Einstein's equation with this, and it's characterized by this metric. And I am adopting mostly plus signature. And with this, I will abbreviate in what follows with the d omega 2 squared. So I think that you all have seen the solution, at least in some basic GR classes. The solution which has spherical symmetry, and that describes a black hole with mass m. So this metric has an apparent singularity at the radius r equals to mg. And this is not a real singularity, but it's the event horizon. Is the event horizon of a black hole. So indeed, if you compute all the invariants that you can compute, for instance, you contract the Riemann tensor or the Ricci scalar, they're all well defined at this coordinate, r equals 2mg. But there is a real singularity which is at r equals 0. So this is just the most basic black hole solution. We are going to build on that to describe other kind of black holes, in particular the one that arise when you have a negative cosmological constant. So I'm gonna tell you now what is close to, like, how the near horizon geometry of this black hole look like, because that would be important to figure out quantities such as its temperature and so on, and to contrast this case of this Schwarzschild black hole with temperature with other cases of supersymmetry black hole that I will tell you about tomorrow that will have a very different horizon geometry. So if you zoom in close to the horizon, so meaning that we can define a parameter xi which is r minus 2dm in such a way that when r goes to 2mg, psi goes to 0, we get exactly a metric of this form. And this part here can be further redefined. So we can redefine a coordinate rho squared that is 8gm psi. So such a way, this metric here, this two-dimensional part, is nothing else than two-dimensional Minkowski space. And then I'm going to write down again this part, which is a simple, like, this is just a two-sphere with radius, this one, with radius this value here. So we see that zooming in close to the near horizon geometry, the metric that you have is just the metric of flat Minkowski space, that this one, flat two-dimensional Minkowski space. It is written in Rindler coordinates, so you can really check that this is, like, you can find a coordinate transformation such that this reduced to this part here. So it's really like pure Minkowski space. And we define this quantity here like 1 over 4gm as the surface gravity. Which is pretty much the Newtonian acceleration at that one observer experiences at the horizon. Notice also that we could alternatively define this in Euclidean signature. So this will become tau Euclidean. And in order for this metric here to be just R2, we need to impose a specific periodicity on this coordinate. It means that tau E over 4gm is to be periodic of 2 pi. Because this acts like a theta coordinate. Because this, in order to retrieve Euclidean two-dimensional flat space, we need to have a metric which is d rho squared plus rho squared, and this will be d phi squared. Phi squared needs to have a periodicity of 2 pi. So in general, so the Euclidean geometry close to a black hole, which is Schwarzschild, indeed close to the horizon approximates flat space, and asymptotically the Euclidean geometry as the geometry of a cylinder. So therefore, the metric itself is a so-called cigar geometry.
What happens if the periodicity is not applied? It still satisfies Einstein's equations, right?
It still satisfies the Einstein's equation, yes, but the fact that you will have a conical singularity.
So physically, what would that correspond to?
Correspond to physically, yeah, in general, your solution will, let's say that you will have a space-time which is not quite regular. You'll have just a conical singularity is what you have when you, well, I don't know how to show it with a piece of paper, but it's something like when you have really like a cone. Instead of closing it.
It doesn't solve the Einstein equation unless you put a delta function.
Exactly, yes, you can also say that. Let's say it solves them in every point except exactly when you have the conical singularity. But so all this to show that in general these solutions here, in order to cap off at the horizon in a regular way, you need to impose periodicity of the time coordinate. So the surface gravity, so a remarkable, let's say, study of Hawking and also all the other people who were responsible for the study of black hole thermodynamics shows that indeed black holes radiate with a temperature which is proportional to the surface gravity, which is the quantity that I really wrote down here. And there also exists some very remarkable correspondence between laws of thermodynamics and laws of black hole mechanics. So indeed, the law of thermodynamics I'm just going to write them down so then you have them all. So indeed, there is a parallel between what you have with law of thermodynamics and the laws that a black hole satisfies in general relativity. So indeed, the first law is parallel in the fact that kappa, the surface gravity, is constant at the horizon. So there exists also a law of relating variations of black hole quantities. Moreover, in all the physical processes, we have that indeed the entropy, the area of the event horizon, never decreases. So this is just a parallel, very powerful parallel between laws of thermodynamics and laws of black hole mechanics.
On the black hole mechanics first law side,
Yes. Mm-hmm.
M, Q, and J are charges measured at infinity, where A is
I'm going to explain what the quantities are. So this is just the mass, like energy, measured at infinity. These are the area of the event horizon, surface gravity, and these are charges and angular momentum, and these two are the conjugate variables to angular momentum and charge. This is the chemical potential, this is the, let's say, the angular velocity for the black hole. So yes, what was the question?
It's just, I always get confused by the fact we can relate things we can measure at infinity to this very special area of the horizon. But maybe it's just me being confused.
I'm not questioning the law, but just.
Yeah, this is something that is valid for the solution. So the solution itself will relate what is. Indeed, the area of the event horizon depends, like if you compute it, explicitly it will depend on the mass and the other parameters of the black hole.
How can an observer at infinity verify this law? They can measure the change in the energy and in the charge and the angular momentum, but how can they check if what the area of the change in the area of the horizon?
Well,
staying at infinity.
No, but also, for instance, these two quantities, you need some input. These two, they are the chemical potential. For instance, this is like the difference between the electrostatic potential at infinity and on the black hole horizon. So you also need some input for that parameters. Unless you decide your gauge field, or you need to set your boundary condition in such a way that, for instance, the chemical potential, the gauge field on the horizon is 0, and then you measure at infinity. But there is some interplay between horizon and the same. Yes, it's these two quantities they're very similar, just that they pertain to different conserved charges.
Is it like related to the covariant phase-space formalism that you pick a Cauchy slice and the true endpoint, one is end on the horizon and the other end at infinity, so that you have some charges localized for the kilowatt. So.
Yeah, so I guess that you need to set boundary conditions. So you need to set, you need to have information from both sides. Let's say, but so all this, let's say, this this is quite this is a lot more than a formal analogy, because indeed, like Bekenstein, indeed proposed the fact that the horizon of the area of the horizon of a black hole indeed gives the entropy of the black hole, given the fact that these two quantities satisfy the same monotonicity law. Moreover, Hawking discovered that once one takes into account quantum, quantum effects, a black hole is not exactly black, but it radiates at a temperature which is proportional to the surface gravity. So indeed, to a black hole, you can associate these two quantities, which are the entropy and the temperature, which I'm giving you the formula here. So then we record them from so indeed, this is the Hawking temperature, which is nothing else than 2 pi kappa, which in the case of a Schwarzschild black hole is h bar over 8 pi gm, and the Bekenstein-Hawking entropy, which is area. I'm just restating all the constants, but for later on, I will set C, H bar, and sometimes even G to be only one, to be natural units. So this is for what concerns a black hole in asymptotically flat space. So the Schwarzschild black hole indeed has temperature, has entropy. However, when it is it lives in a space of in Minkowski space, like in flat space, it has negative specific heat. So it means that it's some sort of unstable for the following reason. So specific heat is defined as this quantity here. And this quantity, if you do the computation for this particular kind of black hole, you get a negative number. So we can also just do the computation here. These both quantities depend on R plus. I'm taking the ensemble in which the charge is constant and it's 0, and also the angular momentum is constant to 0. And for this, given the fact that S is, S is pi R4 plus, and T is equal to 1 with 2 pi R plus. This is a negative quantity, and if I did the computation correctly, it's just R pi squared. So this is negative, and equivalently, the specific heat can also be written as dm in this ensemble over dt. So, and if you want to plot, in particular, the temperature versus the area of the event horizon, or the entropy equivalently, you find something that goes this way. So why is this thing problematic? So indeed, wait.
Or it's a general feature of asymptotically flat black holes?
There are many different Yeah, I will come to this point later. For the moment, I'm just going to deal with the static black holes. So yeah, just to give, so when you add charge, there will be a branch which has positive specific heat, and I will show you later in the graph when I will compare ADS and charged black holes. But so this is problematic indeed, because indeed, when the black hole in general radiates, so it, like its mass diminishing, but it means that the temperature will keep on increasing, so it will radiate even more, creating indeed indeed some like instability in the spacetime. So for this reason, something like, let's say that Schwarzschild is unstable, it is some sort of pathologic in this sort of spacetime. So what does not happen in a spacetime of negative cosmological constant instead is that, oh, sorry. So this will be very different in a space of negative cosmological constant, because when you add a negative cosmological constant, the specific heat of these guys will become positive, at least for some branches of your black hole solutions. So let me explain now how it works, and I will deal with the example of static solution. I will also add some electromagnetic charge, so then we do the case in full generality, or at least for the static ones.
Just to make sure I'm on the same page. The temperature is the temperature measured by an observer very close to the horizon.
Yes.
Okay.
I mean, it's it stays however it is outside the event horizon.
Yeah.
Let me see. Okay, so as I was mentioning, for black holes in anti-de Sitter, however, this will be very different. And I'm gonna explain you how. First, I'm gonna give you the solution of a static black hole with charge and a negative cosmological constant. So first of all, so solutions that I have in mind. So these are asymptotically anti-de Sitter black holes. They are solution of this to the equation of motion of this action. So this number here, like L is the radius of ADS space that is related to the cosmological constant via this formula here. This is what we have in our conventions. So this is the contribution then from the cosmological constant. So if you switch the sign here, of course, you have the Sitter space. So black holes in the Sitter space, they also have some very non-trivial features that I will mention probably in the next days, but will not be object of these lectures. But so the solution of this kind, they are indeed, they have the same form as the static Schwarzschild black hole, but they have different kind of different form of the word factor. So with V of R, which is indeed 1 minus 2m over R. Let me change, let's see if you can see it from here, plus Q squared over R squared, and this is due to the fact that you have F mu, and they have also another term here, which is nothing else than the term which is due to the cosmological constants. And of course, we have also, for the moment, we just deal with solutions which are electric, which means that this is just the value of the gauge field. So I don't know if you can see really from the colors, but basically I think that you already know that this part here is due to the fact that you have a non-trivial charge. This is just the ADS static, like a static black hole, which is the ADS Reissner Nostrom. This term here is due to the fact that you have a non-zero cosmological constant.
You said change them to 1 now?
Yes. So from now on, I will set all the H bar, C, and G to 1. So for these solutions here, these solutions are a bit more complicated than Schwarzschild in the following sense, meaning that only for certain parameters, you'll have a black hole, which is like a singularity, which is shielded by an event horizon. So the singularity is still at R goes to 0. This is really like a pure, like a generic feature, but it's also coordinate independent, like meaning that there is still a singularity. It's not an apparent singularity. And to find location of the horizon, which we will call R+, you have to solve the quartic equation. So this is the horizon, satisfies this property. So in order to find the horizon for anti-de Sitter black hole, you need to solve this equation here, which amounts to solving a polynomial equation of fourth order. So if you plug it into Mathematica, yes, but you can find solutions to this equation in a closed form, just that they will not be very pretty, will be very big. And you'll have 4 of them, usually 2 of them are complex, and other 2 of them will be real and will be the outer and the inner horizon of your black hole. So this is pretty straightforward, albeit can be a bit cumbersome to find the roots by hand. And also all this.
Can you actually have 4 solutions, like 4 real solutions?
No, I think that they're just how to say, they're not allowed for these sort of things. You have only you have the structure is still that you have an inner outer horizon and then nothing else. Even if though some people also attach some meaning to the other complex roots, because there are some let's say some observations for which you can take the product of the 4 areas, even the complex one. The complex one will be conjugate. Eventually, the product is fully real, and this is only function of the quantized charges. So
The product of the areas.
product of the areas, even of the complex of the area that you get even from the complex roots. So it seems that they might play a role in some way, in some other kind of microscopic counting, but for the moment it's not clear what is their physical meaning. But at least for a certain range of parameters, M and Q, and for fixed cosmological constant, you have 2 horizons. You can compute also the entropy of this black hole, which again I'm setting all the quantities like the G, all the units to natural units. And I'm also gonna give you here the temperature of the black hole. So the temperature of the black hole can be found in the same way as I was mentioning before, just by turning your solution into Euclidean signature, zooming close to the horizon, and finding out the periodicity of your Euclidean time coordinate. Just that it's a bit more involved here because the warp factor is different, but the procedure is the same as I outlined before a couple of blackboards ago. So entropy is this one, this is the temperature. So remember that for the Shortshit solution, this was the graph, the temperature versus entropy. It had a negative slope, and this was reflecting on the fact that the specific heat was negative. Now we can plot this thing for let's say for an anti-de Sitter black hole. Okay, I can just maybe. So let's do first the case in which you have an uncharged black hole. So we set first Schwarzschild ADS. So we set Q equals 0 for the moment, no charge. You find that if you plot the temperature versus the area, entropy, temperature, you find a very different behavior. So meaning that you have 2 branches of black hole. So this point here is when, like it happens when R plus squared is equal to L squared over 3. So this is the inflection point. So you find 2 different black hole branches. One it is called small, and the other one is large. 2 different black hole branches. It's called small and large with respect to, like, depending if their entropy is, let's say, comparable or smaller than other than with respect to the ADS radius. But basically, you see that here for large black holes, you have a positive slope of this graph, which means that the specific heat is positive. So for this sort of black holes, these solutions are indeed like unstable, and they can be in equilibrium with radiation at a fixed temperature. So indeed, for this sort of black holes, well, what is in general, how we would like to say is that the negative cosmological constant has some sort of stabilizing effect on black hole physics. And indeed, anti-de acts some sort of like a box that keeps the radiation in, and in which, like, given the fact that you have a cosmological constant, these black holes, if they're sufficiently big, can be in equilibrium with thermal radiation at a fixed temperature. Therefore, the canonical ensemble, an ensemble of fixed temperature, is well defined. So this is indeed like the small, large black holes. But if you also have charge, situation becomes even more interesting. So ADS Racine-Ostrom. It's an Ostrom black hole. We need to actually divide our treatment into two regimes. So there is a critical value of the charge, so which we call QC. Well, let's say Q critical, which is defined in this way for ADS4 black holes, for which if you are like above, if your charge is above, then Q critical, this is actually what happens. So the temperature is monotonic with respect to the entropy. But if you are below a certain threshold, something very interesting happens. Q smaller than Q critical. You have actually three possible branches. So this is the large. This is the medium. And this is the small. So the small goes all the way up to here. Medium goes all the way up to here. And then you have the large black holes. So in this sort of configuration, you can recover what we said before. So the appearance of, like the presence of charge makes the appearance of this branch. Because before, for Schwarzschild ADS black hole, we only had these two branches, right? So the presence of charge is responsible for this branch here. The presence of cosmological constant is responsible for this branch here. Because the black holes that I denoted as medium here, they're nothing else other than what you will have as a Schwarzschild. So this is, if you have charge, you get this. If you have cosmological constant, you have this. If you don't have this, you just have the Schwarzschild, like asymptotically flat black hole, which is unstable. So as you can imagine, the medium black holes, the one that has a negative slope, they are unstable, while the other two branches, small and large, they are indeed stable. They have positive specific heat. Just let me see how am I doing with time.
So in flat space, if you added charge, do you then get stable small black holes, or does it not quite apply?
Yes, pretty much I think that it would be like this. So this is also, yeah, due to the fact that, this point here is the point of zero temperature. So the ones that are general ones you have, especially when flat space, being extremal is a lot of times connected with being supersymmetric. So in a way, you expect some sort of stability, at least closer to here.
But in the flat space context, in what sense, what is the scale with respect to which these black holes are small in flat space?
In flat space?
In ADS large and small, you can compare the ADS radius.
Yes.
To the size of the black hole. So when what's happening in flat space-time? What's the critical?
I think what you have there is like. Okay. I should think about it, but I think that. Yeah, I think it depends on their mass and the charge probably. I will need to just think about it to see whether there is a ratio or not for that. But okay, so in the case where you have an anticycler, you have up to 3 branches here, and you can compare. So in this case, you have multiple competing branches with different, for instance. Oh, sorry. Here I just didn't put the temperature versus entropy again. So there are many different branches that compete in the thermodynamic ensemble. There are this and this. So for instance, if you set a temperature, which is here, you have 1, 2, and 3. The medium black holes, in general, they are not there in the ensemble because they have negative specific heat, so they will not play a role. But in order to figure out, actually, which ones will dominate in our ensemble, we need to see which ones have the lowest free energy. So the free energy in this case is we set in an ensemble in which the charge is fixed. So we have for Q fixed, the thermodynamic potential that needs to be extremized is the Helmholtz free energy. You can check this coming from the first law of thermodynamics. You see that if the charge is fixed, this quantity here is extremized. So if you compute this kind of potential for each one of the branches that we have here, we find something very intriguing. So this is free energy versus the temperature. So the first branch here, this is the small branch, so it goes all the way up to here. This is I'm going to it small. The medium black holes, they extend all the way here. And the large one go from here all the way down. So you see that all these three branches, you can plot them. These are very easy to do, and I actually prepared an exercise. You can do all these graphs in Mathematica using, for instance, parametric plot. They're very easy to do. And so this is what happens with the free energy. So the system would like to minimize its free energy. Therefore, the configuration that will dominate the ensemble will be the small black holes up to this point here. But then, at this point here, then the configuration will be favored will be the large black holes. So the large black holes will be this one. So at this point here, at this point here, we call it temperature of phase transition, because there is a first order phase transition between small and large black holes. It means that up to here, the small ones have the lowest free energy, and from here onwards, the large ones will be the one that dominates the ensemble. The medium ones, as I was mentioning, they have negative specific heat, but also they are never favored thermodynamically, meaning that their free energy is always higher than the second two. So they will never appear in our ensemble. Just let me mention that here, nothing really, there is only one temperature for each value of area. So in this case, the phase, the diagram, it's nothing really, it just goes monotonically. So this case is a bit of a boring case where nothing really happened. It's a crossover. It's not really a phase transition, while here is really a phase transition. And you can actually check that the phase transition happens exactly at the area, at the point like at the temperature, such as the area under this curve here is exactly equal to the area that you have here. So, and this for you, it should ring a bell. It's like the Maxwell construction that you have for the liquid gas phase transition. So indeed, you can interpret, and this is okay, I skipped all the references, but you can ask me later. This was found first by Chamberlain et al. In 1999. So if you have to look at Inspire, you can search for Chamberlain and Paran. The title is Catastrophic Holography, because indeed you can check what are the critical exponents of this phase transition, and they call it catastrophe because they use some results from catastrophe theory. But in any case, so this is a very good paper in which people discuss this phase transition, and also they discuss how to see the similar phase transition in an ensemble of fixed potential.
So what's happening below that point? Then you just have thermal radius phase.
Which one, sorry?
When this graph intersects the x-axis. So there's no black holes below that. So then you just have the thermal radius phase below that.
Yes, but I would say so. This is an ensemble for which you fix the charge. So you see, you will not have empty ADS with charge, because it will be either a black hole or a naked singularity. So in a way, let's say it stops here. Yeah, so maybe I should have just not, okay, that's. So in this case, it's boring because nothing really happens. So if you have to look at the phase diagram, then if you have to do a schematic representation of this, like Q versus temperature, you have a phase diagram of this point, in which below a certain charge, you have two black holes and a phase transition between small and large black hole up to the critical value of the charge, which is exactly like it's related to the length of to the cosmological constant, and this will be a crossover. So no phase transition above a certain threshold here, but a crossover, but a phase transition between small and large when you go below this threshold.
A crossover meaning that I can have any mass for the black hole.
Yes, exactly. So because you can have, what you say pretty much, you can have every temperature. I mean, every mass, provided that you satisfy some sort of extremality condition. So provided you have a horizon. Okay, so this is the simplest example of phase transition. Well, actually, it's not the simplest one, because the simplest one will be the Hawking-Page phase transition, which I thought that probably I would not get in time to explain, but if you want, let me see how am I doing with time. Yeah, I still have some minutes, so I can quickly go through it. Are you familiar with the Hawking-Page phase transition? Maybe, or okay, good. So then at least I can just do it. So. In this lecture, I wanted to make some sort of parallel between the thermodynamics that you have in Minkowski and the thermodynamics that you have in de Sitter. And already you see that just by adding cosmological constant and charge, you have a phase diagram which is much richer. You have a lot of things that pop out. And in the dual field theory, you can indeed interpret this phase transition as a liquid-gas-like phase transition. Already also in the case without temperature, however, already in the case in which you have like a Schwarzschild ADS black hole, you have a phase transition as well. In that case, we keep again, so the charge is set then to, we set the charge to 0 because we want to work with uncharged black holes. And the one that I'm going to describe is the prototypical, let's say, prototypical phase transition that you can have. And it was found by Hawking and Page first. And it also like shows you how the thermodynamics of this anticipated black hole is richer, let's say, because already in the case of a Schwarzschild ADS black hole, there are two configurations that compete in your thermodynamic ensemble. So we have one, which is the Schwarzschild ADS black hole, or at least the large branch, because we know that the large ones are stable. Let's say, I will put it large branch. And the second configuration they are competing is thermal ADS. So ADS with a field with thermal radiation. So already in that case, or already in this case, we can have indeed a phase transition. So we consider first the action for these two. So this is the action. This is just Einstein-Hilbert plus the cosmological constant. As I was, okay, I erased that, but you see that the cosmological constant was lambda minus 3 over L squared. So indeed, so a solution, so we need to compute then the on-shell action, because the on-shell action will be indeed the thermodynamic potential that tells you which configuration dominates. The on-shell action in this case is really like in the case of ADS Dresden-Ostrom black hole with specific boundary conditions such that your charge is fixed, reduces exactly to the Helmholtz free energy. So it's equivalent to study all of that, like they are equivalent thermodynamic potentials. So to compute the on-shell action, we have to first plug in, we can plug in the equations of motion. So I need a solution to the equation of motion, to the Einstein's equation, satisfies this. So we plug in So the shell so we just plugged in the constraints that is required for solving the equation of motion inside this. So the on-shell action for a solution is just proportional, sorry, I made a, okay, minus 2. So it's just proportional to the volume of this, of the solution itself. So this is just the integral over the determinant of the metric.
What about the Gibbon-Sutton term?
Hmm?
The boundary term?
It's taking, so yes, we were gonna, it's a bit sloppy. So the Gibbon, so let's say, if you compute this action here, you get a contribution which is infinite. So we have to, first of all, like set a cutoff, a radial cutoff, which is large, we call it R0. We are gonna compute solutions with the same boundary conditions, so we're just gonna take the difference between two on-shell action, the on-shell action of thermal ADS and the on-shell action of short seal. In that case, the divergence gets cancelled because we take the difference between the two. However, if we wanted to get a finite, finite value for the renormalized on-shell action, we have to renormalize it, in particular adding the Gibbon-Sutton term, and also adding some other counterterms, which are function of some invariants, like curvature invariants on the boundary, to make this object here like well-defined and particular finite, once you remove the cutoff.
The Gibbon-Sutton term will be different for the solutions, right? Because it's in the curvature is different.
No, we are gonna do it in such a way that they are different because we are gonna set exactly the metric with the. I'm gonna show you now if you want. We're gonna do it in such a way that indeed the thermal circle and the other features of the solution, they're just exactly the same asymptotically for the two solutions. Otherwise, we will not be able to compare them. So this is the value for the on-shell action that we get. We need to plug in the various solutions, and as I was mentioning, we have to indeed set a radial cutoff, so regulate with a cutoff. That set it R, big R. So this thing, we call it V of R. So we have to compute it in two different solutions. So this is for ADS. So I already, this is the Euclidean on-shell action. So we also performed a weak rotation, which I also didn't mention. But basically, for anti-sitter, we have to integrate this from, on the Euclidean time coordinates, which has periodicity beta 1. And also we integrate the radial coordinate on the radial coordinate. It goes from 0 to the cutoff R, and then we integrate on the two sphere. For the black hole itself, the thermodynamic potential instead, it is again like an integration over all the variables, but it is slightly different. The slightly different extrema of integration. Oh wait, no, this is like. Well, you see what I mean here. This is like you need to integrate over. D theta sine theta d phi. So for the black hole, is like in Euclidean, is a cup geometry, as I was mentioning before, is this cigar geometry. So the extreme of integration are from R plus to the cutoff R, and this is exactly on the temperature of beta 0, which is the temperature of the black hole. So these are the two thermodynamic quantities that we have to compare. Of course, as someone was saying before, we need to make sure that the solutions have the same boundary conditions. That's a very important point. In particular, they need to have the same boundary geometry, and which means that we have to really make sure that beta 1 and beta 0 are related and they give the same length of the Euclidean time circle at infinity. Doing so means that we have to relate beta 1 and beta 0 via this formula here. So this is like R square. Okay, this makes pretty much the length of the time circle of ADS the same as the one in the black hole. So then the geometry, once you go to the boundary, is really the same. They really match as it should be. So at this point, we are really now able to take the difference between the two different potentials that are here. So we do this then. So we define the difference, which is the limit R goes to infinity of V black hole R minus V ADS R, which is equal to 4 pi 4gn. Okay, maybe this. Okay, I'm just gonna erase this quantity, so it's only equal to pi multiplied by L squared R plus squared minus R plus the fourth over 3 plus squared plus L squared. So remember that for the black hole solution, we had to integrate between the radius of the event the integrator radial coordinate from the radius of the event horizon to the cutoff. But the upshot of this is that once you remove, let's send you the cutoff to infinity, the difference between these two thermodynamic potentials is finite, and so you can study it. Here, we see that for R plus small, ADS has lower free energy. ADS is then favored. And for R plus big, a black hole is favored. In other words, the sign of the difference here changes when you raise the temperature, in particular when you vary R plus. So for a small value of temperature, the ADS space-time field with radiation is the one that indeed dominates the ensemble, while instead for high temperature, the large black hole indeed is favored. And this is the so-called Hawking-Page phase transition, which was then interpreted by Edward Witten as a confinement-deconfinement phase transition. So indeed, in this case, the black hole is the deconfined phase. And then the anti-Sitter field with thermal radiation is the confined. And there are other different kind of, how would you say, like proof that indeed in this regime, for instance, the Wilson loop has an area law, which means that the system is in a confined space. So, okay, let me see how we're doing with time. Okay, I think it's pretty done. So, okay, I think that this, so with this, I think the lecture is pretty much concluded. But just what I wanted to give you as an upshot, which I already did during my talk, I believe that indeed, so both for the case of uncharged black holes and also in the case of charged black holes, we have seen that the fact that there is a cosmological constant makes up for the existence of many different black hole branches, and phase transitions can occur between different black holes. And this phase transition can interpret in various ways, depending on the nature of the boundary condition, the nature of the solution, have different interpretation in terms of the dual field theory. And with similar solutions of black hole, but just more complicated with scalars, and in particular with charged scalars and so on, people also managed to indeed to model superconductivity, for instance, by means of black holes with scalar hair. So there exists indeed a particular temperature for which a black hole with scalar hair is indeed favored with respect to a black hole without scalar hair. And the fact that there is a scalar hair, it manifests itself in some sort of like a creation of a condensate of Cooper pairs, which means that the solution is superconducting. So this is another example. I can give you more probably in the discussion if you want. But so just to say that these are features that do not occur instead for asymptotically flat black holes, and they make indeed the ADS black holes very special in this regard. So okay, this is all what I wanted to say for today.
So the phase transition between ADS and black hole is interpreted as a confinement, deconfinement.
Yes.
What about the ones that you showed earlier, which is just between small and large black holes?
Yes, between small and large. This was it was interpreted as some liquid-gas-like phase transition. This is more visible in the case where you have a configuration with scalars. So the expectation value of the operators in that corresponds to the asymptotic modes of the scalar really is typical of the liquid-gas phase transition. So yes, it's a bit unfortunate that after all this work we recover water, but of course people have a...
Like the critical endpoint in the water phase diagram.
Exactly, yes, when you have a crossover. So it's really like the scenario is really typical, it's really similar to the isotherms that you get for a van der Waals liquid. The one for which we have like pressures versus, so this is in an ideal gas, but then in a real gas, the isotherm starts going this way. And the phase transition really appear when this area here is exactly equal. So the similarity is striking.
So does that say they're in the same universality class?
Yeah, I would say so.
Did you say that you can't have this type of scalar condensation in flat space?
So let's say for that, I mean, I don't think that people, I don't know what's the status of, because I'm mostly familiar with the supergravity, where the charged scalars are mostly given by hypermultiplets. And in that case, I don't think that solution with these charged scalars have been found. But I will need to look up for it. But usually these solutions, like with charged scalars and so on, in anti-jitter space, were found not analytically, numerically. So perhaps some similar study has been done in asymptotically flat, but I will need to see. For sure, I believe that in theories of supergravity, mostly because people were interested in supersymmetric solutions, I think that solution with hypers, they're a bit more tricky. At least in the analog setting, I'm putting a lot of caveats. These are in 4 dimensions and in a specific scenario. So I'll need to come back to you. Maybe I can do a bit more research and see.
If I recover liquid vapor transitions, is it, I think that the dual PDS4 is some sort of using model in 3 dimensions?
I mean, all this, so the dual field theory to this sort of black holes that I'm studying is ABJM. So it's a 3-dimensional superconformal Chern-Simons model.
Does it float, is it from the same universality class as the Ising model? Or?
Well, I would say that it's quite different from the Ising model.
But because you are discussing the first order phase transition, not second order, I guess. So
the phase transition that we have.
Indeed, my question is related to his question: is whether there are also critical points in these phase transitions in gravity, whether there are second order phase transitions.
There is a second order phase transition once you're really at the tip, let's say. So I don't know if you, let's see. So if you're really, I don't know if you remember, I plotted this graph at some point. This here. So when you're really here, the phase transition becomes second order. So this corresponds to having, the free energy starts being like this, but then also starts being less and less until it kind of is like this. Okay, but in this case it happens when when you are really set on this particular value here.
I mean, in more exotic theories like Vassiliev gravity, which is supposed to be able to try criticalizing model in 3 dimensions. That's probably an example.
Yes, I think at that point there one can explore the question that he was asking about the dual universal models.
Okay, well, if there are no more questions, then that concludes today. And, thank you, everyone.
Thank you.